Hey guys, in this video we're gonna demo into metric space. So actually we've already dealt with problems about metric space because for example the real line that we constantly talking about, real line is actually a kind of metric space. And I just want to give you some further or general understanding about metric space because I feel like it will be easier to understand some proofs or theorems if we kind of know what the metric space is and something like at least we will expand the all the definitions and theorems we've already learned to the two-dimensional case because we've already dealt with one-dimensional case, which is a real line, right? But we want to further talk about things on two-dimensional case, which is actually complex plane. So in this video, I'm going to show you what is metric space, and hopefully we'll also introduce some definitions and theorems on the two-dimensional case on R2 space. And maybe not in this video, but in the next one, I'm gonna introduce another important character of a set, which is compactness. Okay, now let's get started. So first I'll give you the definition of metric space. So what is a metric space? Suppose we're given a set X and we call all the points of the set we call all the points, we call all elements of the sets points, right? We call elements of the sets points. So a set is said to be a metric space if we will have a distance function. So to be a metric space, you will need firstly a set. And secondly, it says if for any 2 points PQ of X there is associated a real number distance of PQ, so we will have some kind of distance. So the point is how are we gonna define the distance? How are we gonna calculate the distance between 2 points? So we need distance. In fact, we need some kind of distance function, which is also we just call such kind of distance function a metric. So this is why we call it a metric space, because it's a space. Well, it has a set, right? And it's a space associated or equipped with a metric. So the metric will have satisfy 3 principles. So first is that the distance between P and Q should be 0 if P should be larger than 0 if PQ are not equal. And if PQ are equal to each other, so the distance between the point and itself is 0. The second principle is that the distance between 2 point PQ is equal to distance between QP. So if you interchange 2 points, the distance between them will not change. Okay. The third principle is the distance between PQ is smaller than if you take another point between PQ R and you somehow detour it before you just go from P to Q directly, right? But now if you detour from P to R and R to Q, and of course the point R can also be put on just between PQ on the straight line of PQ. But if we take R other than the outside the straight line PQ, we can actually get the distance between P to R and R to Q. The sum of these two distances will be larger or equal to PQ. Okay, this is very simple and straightforward, right? So just to mention that any functions with these three principles properties is called a distance function or a metric. So in fact, for a metric space, we'll first find some set, and the second we'll define a metric. Okay, so here the metric, the metric in this case is to give a function to find the distance between 2 points, right? And although we've only get exposed to the real line space, but actually I've seen some interesting examples I remember it's called Manhattan distance. So I think it's a definition quite often used in the computer science area, because I read it on some relevant papers. So it's something like you only calculate the horizontal and the vertical distance between 2 points. So it's like you're given a graded space or something. No, so the space is given, and you are also given some grids on that plane. And so if you are gonna calculate the distance between PQ, you're not gonna go directly from P to Q. Instead, you will only count those how many vertical lines and how many horizontal lines you have. And also we sometimes will give the different weights to different lines. So maybe for vertical lines we give a weight for each segment 5, or for horizontal lines we give 3, weight 3 for each segment. So this is just a kind of interesting example, and there are a lot of kind of metric space, and some are really bizarre. So if you you can do some research on it or just have fun. It's quite interesting. So okay, here we have 2 remarks. So although the metric space, the distance function, as I said before, can be very bizarre, or there are a lot of different metric, but in this course, in the videos I'm gonna present to you, we will basically focus on real line and the the complex plane, these 2 kind of metric space. And the distance function, we will use simply the Euclidean distance. So it's just the distance between 2 points in the space is simply the norm of x minus y. And also another thing is that if we are given a metric space X, and if we take the subset of a subset Y of a metric space X, it's just automatically become a metric space. And well, for a metric space, you have to find 2 things. The first is a set, right? Now we've already given a subset Y, so we already have a set. The next thing is to find the metric, right? What is the metric of the subset Y? We just use the induced metric from the original set X. So the subset Y is also a metric space, and its metric is induced from X. Okay. Now next, let's move on to some definitions. Some of them were already introduced in cases on real line, but some are not. So we're gonna take a look at them one by one. The first definition is about neighborhood. So what is a neighborhood? A neighborhood of a point P is a set NRP which consists of all points Q such that the distance between P and Q is less than 0. So the notation here, P is the point, and R is the radius of the neighborhood. So if we consider this definition on the complex plane, which is a two-dimensional plane, it's just if we take a point P here, and we are gonna have a radius R. So the neighborhood of P with radius R is all the points such that the distance between P and Q is less than R. So it's simply the circle, right? I'm sorry. Here's P and here's R. So it's simply the circle, but since the distance have to be smaller than R, we don't take the boundary of the circle, right? So it's something like an open circle because we don't take the boundary. But we will define open in the next in the following definitions. Okay. Now let's move on to the second one. A point is a limit point of V. So now we are given the set E. A point is a limit point of V if every neighborhood of P contain a point Q other than P such that Q is contained in E. If you compare the definition here to the definition we previously introduced on the real line case, so here it said every neighborhood of P. Actually, every neighborhood of P can be translated into every radius, right? Because you want to find the neighborhood of P. You've already given the point P, which is the center of the circle. The next thing you need to determine is just the radius, right? So it's the same, saying that every neighborhood of P is the same. It's the same to every radius, right? So every neighborhood of P contains a point Q that is lying in E. It's pretty much similar to the real line case where every intersection of the small set A minus epsilon, A plus epsilon, and the intersection of the small set and the original set A is not empty, and the point A is not counted as the point that lies in the intersection, right? And here's the same because you will always find some point in the neighborhood, and the point cannot be the point itself. The point cannot be the limit point that you want to prove. Okay. C. If here's another definition we haven't introduced in real line case. So if P is contained in E, so P is the point of V, and P is not a limit point of V, then we call P a isolated point of V. Well, so it's very people tend to think of isolated point just if it's not a limit point, it's an isolation point, right? But I think you might have to take care, because here remember I've already said that in the previous video. I remember I mentioned that the limit point of a set can be some points that do not lie in the set, right? But here but here to be a isolated point, you have to be a point of V. Okay, so I think this is what you should pay attention to. Okay, and D. So now we finally get to the definition of closed set. So it is closed if every limit point of V is a point of V. This is simply the restatement of a closed set definition on the real line, right? E contains every limit point of V is the same to that A contain is closed if every limit point of V is a point of V is the same as if E is closed if E contains all its accumulation points, right? So we're not gonna further explain that because it's the same. Okay, we move on to E. We finally get to the interior point. So a point P is an interior point of V if there exists a neighborhood N of P, such that N is contained in E. Still, it's very similar to the case on real line. It's pretty much the same because in the real line case, you take a small set that is contained in the original set. But now you just take a neighborhood of, right? Taking a neighborhood of P, such a neighborhood is contained in E, right? So I think they are pretty much the same. F. So now we're finally move on to open. So what is an open set? It is open if every point of V is interior point of V. It's just the same with the case on the real line. So G, the complement of V is the set of all points P such that P is contained in the complement of V is a set of all points P that is in X and such that P is not contained in E. So the complement of a set is a set that contains all the points that lies in E, but lies in X but not lies in E, right? Okay. So H is bounded if there is a real number M and the point Q contained in X such that the distance between these 2 points PQ is less than M for all P that lies in E. So you can just imagine on the two-dimensional case, if a set E is bounded, then you can always find a circle that contains all the points of E, right? Because you can just to find such a kind of bound, you basically try to find some radius that can, so that the circle that you draw or you are looking for is big enough to contain all the points of E, right? And actually you can find that because E is bounded. Okay. So, okay, another character of a set is about the density. Okay, density. So, E is dense. E is dense in X if every point of X is a limit point of E or a point of E, or both. So if a set is dense, then if a set E is dense in X, that is to say every point in X, pay attention to here, every point in X is a limit point of V or is a point of V. Okay, this is actually a very strong condition because is either lie in the set is a point of X either just lie in the set the subset E or its limit point. Okay, so actually I think you will find that the definition on these two those definitions but on metric space and that we mentioned in the previous case on real line is pretty much similar. It's actually the same because real line is just a case of a metric space, right? So it has to be same. And well, neighborhood we don't actually mention about neighborhood on real line, but you can just imagine it as the neighborhood on the real line is just some segments, line segments, right? But the neighborhood on the R2 space, so the complex plane is circles, but we don't take the boundary of the circles. So if you like further consider it on the three-dimensional case, the neighborhood is kind of like can be a ball without the boundary, right? Okay. Now let's move on to some theorems. Most of them are pretty simple, and I'm just gonna show you the theorem and some very simple proof. Okay, so every neighborhood is an open set. Actually, we've just talked about it, right? Because, well, how to prove a set is open set? Just by definition, every point in that neighborhood is an interior point of it. And it is, right? Because, well, firstly, if we take a neighborhood of P, we want to show it's an open set. So we want to show that every point in the neighborhood of P, say NRP, every point in the neighborhood NRP is actually an interior point. So if we take any point Q here, and how we're going to show it's an interior point? We show that, well, by definition here, what is an interior point? It is an interior point if there is a neighborhood such that the neighborhood is contained in the set, is the original set, right? So to show that Q is the interior point of the neighborhood of P, we just need to find some radius or some neighborhood such that the neighborhood of Q is contained in the original set, which is the neighborhood of P, right? And we can find such kind of neighborhood because we only need to take the radius of the small neighborhood to be smaller than the radius minus the radius of P minus the distance of P and Q, right? So RQ should be smaller than the radius R minus the radius R, which is the radius for the neighborhood P, minus the distance between P and Q. So now we prove that take any point in the neighborhood, it is an interior point. So every neighborhood is an open set, right? Okay. So next theorem is that if P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. Okay. So how are we gonna prove that a set contains infinitely many points? We're not gonna count or directly prove that it has infinitely many. Instead, we're gonna show that it cannot be finitely many. So we prove by contradiction. Well, suppose we now have a neighborhood of P such that contains finitely many points of V. So since it's finitely many, we can write it as Q1, Q2, until Qn, like this, right? Okay, so the Q1 to Qn are all the elements in the neighborhood of P. Okay, so now we're trying to find the minimum distance between P and all these points. So we let R be the minimum value of the distance of PQI, where I is from 1 to n. And while we trying to find the minimum distance, well, the reason we did this is that we want to show that there are infinitely many points But now we want to show it we want to prove it by contradiction. So we suppose there are only finitely many points. So we want to show, we want to deduce from the assumption to the contradiction that P cannot be a limit point. So how are we gonna prove that P cannot be a limit point? So by the definition of a limit point, right? By definition of limit point, we show that we cannot find. We show that there exists some neighborhood such that we cannot find a point other than P itself, right? So how are we gonna find that neighborhood? How are we gonna find that neighborhood? We just need to find a neighborhood that contain that not. We need to find a neighborhood that contains no elements other than the point itself. And now we are given finitely many points of E, right? And since it's finitely many, we can find the smallest distance, right? And if we take a smaller distance than the smallest distance, we're not gonna find any other points, right? Because all other points have distance larger than R, right? Okay, that's the reason why we take R to be the minimum distance of PQI. And now, if we get that NRP, where R is a minimum distance, contains no point of E, right? So, in this case, P is not a limit point, right? I'm sorry. Here should be contains no point of V, no point of V other than P, because we don't take points on the boundary, right? The point that give the minimum distance QI is lying on the boundary of the circle, but we don't take that point into account. So there is no point of V other than P. So now we prove that P is not a limit point, which is a contradiction. So if P is a limit point of a set E, then every neighborhood of P must contain infinitely many points of E, right? It's very simple and clear. Okay. Now, the next term I'm not gonna prove it very formally, but or rigorously, but we are gonna I'm gonna show you some counterexample to give you some further understanding of it. So, A, the union of open sets is union, and B is that intersection of closed sets is still closed. But C, we'll say finite intersection of open sets is open. You have to pay attention here. The intersection of open sets for intersection of open sets to be open, the intersection must be finite. Here, finite intersection means finitely many open sets to intersect with each other, and the result will be open. And similarly, we will have a finite union of closed set is closed. So I'm gonna give you two counterexamples. The first one is, well, if we are given intersection of full negative 1 of n, comma 1 of n, and and n is from 1 to infinity, so we are given infinitely many intersection of open set, right? And the result of the intersection is 0. A set that contains only one element 0, and it's very clear that it's not open set, right? Okay. The second one is a counterexample to D. So if we are given infinitely many union of closed sets, like the union of 1 over n, right? So it's like the union of 1, 1 over 2, 1 of 3, blah, 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 1 of n, blah blah blah, or the union of this. But you will see that actually only 0 lies in the union of the union of the infinitely many sets is not closed because 0 lies in its closure, right? As n gets larger and larger, 0 have to lies in the 0